Alright guys, so now we get into chapter 2.1, the start of a new chapter. So we're done with the review from earlier on. Chapter 1 was all review. However, I do encourage you guys to look over slope because slope will be an important factor, and I guarantee you it'll be on the midterm and it'll be highly emphasized. So make sure you're comfortable with doing slope, point slope form, slope intercept form, general form, all of that good stuff. So 2.1 is all about functions. We've heard of functions before. We hear it all the time, especially in mathematics. When you hear functions, you might think of something like x squared plus 2x plus 5 or whatever. However, that's not what we're going to define it as. We need to actually have a good definition. And the definition I will use, a function, I have to give it a name. So let's say the name of the function, let's make it simple. Let's call it f. Let's call the function f. A function f is a rule. Oops. It's going to be a rule that you have. It's a rule that assigns each element x exactly one element f of x, where x is in set A and f of x element set B. So the idea is a function f is a rule that assigns each element x exactly one element f of x, where x is the set A and f of x is the set B. So the idea is, let's take a collection of objects. Let's take a collection of objects. 1, 2, 3, 4. Let's call this set A. Well, a function is a specific rule that will assign each element in set A to exactly one element in set B. Let's say this is 1, 2, 3. So a function might be, hey, I'm going to get 1 and assign it to, let's say, the number 2. Boom. I might get the number 2 and I might assign it to the number 2. I might get the number 3 and I might assign it to the number 2. I might get the number 4 and assign it to number 3. And in this case, look at every single one of your elements in set A. Each one of them have exactly one output. Even though the element 2 and 3 in set A matches up to this number 2 in set B, each individual element will only have one output. The other ones might have the same output, however, it does not defy our definition. So let me give you a case where our definition is defied. Let's take another example. Let's call this set A. This time I'm going to draw in terms of diagrams. Let's take this set B. Well, let's take some numbers. 1, 2, 3, 4, 10, 20, and 30. Let's say I assign 1 to 10. But then I assign 1 to 20. I assign 2 to 30. I assign 3 to 30. 4 to 30. This is not a function. And why is it not a function? Only because of this guy right here. Literally, this guy messed it up. The first element. If you look at your first element, it got assigned to 2 different numbers. So it's saying that, hey, the number 1 is for the number 10, but also for the number 20. We can't have that. It has to be to a single output. So this is when we get into some, translation of these notations and whatnot. I use the word f of x, f of x. We got to know what it means. So the term f of x is read as f of x. This is not f multiplied by x. No, this is not multiplication. This is not. So I'm going to write a remark. I hope you guys write this down. Not multiplication. In fact, You can't even play with much math with this guy. Like, you can't really, if I did 3 times this, you can't really multiply 3 times x here unless you have special types of functions that we'll talk about eventually. So, you want to treat this as a single term. Now, there's a lot of names for this, but normally the x itself, we call that the preimage. And then we call the entire f of x as the image. Why? Because you have your preimage first, and then after your preimage is used, you have your image. In particular, with this definition we have earlier, I want to give you kind of my taste on a definition for this that I think is very nice. I like to treat functions as machines. In particular, I want to take a machine that's very similar to a microwave, or how it looks. Let's suppose I have like a microwave, kind of. All right, this is a microwave. Now, the idea of a function, the function is this microwave. I don't know what it does. You do not know what this microwave does, or this microwave looking machine. I do not know what it does. So whatever I throw in, I don't know what's going to happen. Let's say I decide to get a collection of objects, let's say fruits. This is my domain. Let's say I get a domain, fruits. I decide to throw in a banana. I throw in a banana. All right, I threw this banana inside the machine. After I threw it inside the machine, it might spit out, I don't know what it does. It might spit out a car, a Honda in particular. So it might spit out a Honda. Now, realistically, that might not happen. However, this is the idea of a function. You have an input. This is called your input. And then once you use your input, or you place your input inside your function, so your input is called x, you throw that thing inside f. You throw that side in here, and then what it's going to spit out is a Honda, or f of x. This is called your output. Output. Same idea with preimage and image. Your input is your preimage. Your output is your image. Your preimage came first, and then after you threw it in the microwave, it became your image. You threw in an input, you throw it inside your f, it's going to spit out an output. The problem is, before we throw anything, this is just a simple function f. We don't know what it does. Unfortunately, in mathematics, you have to throw an object inside your function to know what it does. You have to. If you don't know what your function even does. So, in this case, all the possible fruits right here, the things that I can throw inside the microwave, and I'm telling you, I can only throw inside fruits. These are called your domain. All possible x. We've talked about this already for function f. All possible x values where your function works. That satisfies your function. What's your output, though? Your output, we have something called the range. The range, all possible outputs. They're all possible outputs you can get once you throw something inside the microwave. So in set builder notation, you might see the range of f as equal to, hey, it's all of the objects. Let's say your outputs are all cars, for instance. It's all the cars such that I threw in a fruit. It's all the possible cars I can get if I threw in all the fruits possible. So even though I say all possible cars, I might not be able to get, let's say, a Toyota, if there's no fruit possible that can give me a Toyota. So it might be all the cars excluding Toyota in that case. So I like to just imagine, hey, I'm throwing an object inside this machine and it's going to spit out some sort of other object. All right. And another term, so we have a lot of synonyms in general. Input, we can call it preimage. There's another word we can call it. We can also call it the independent variable. And we can call our outputs dependent variable. And why can we call it that? Your independent variable is just the fruits itself. I throw it inside. However, I can only get these vehicles or cars if I throw in a fruit into my machine. So that's why they depend on what fruit I threw in. However, the fruits do not depend on the cars whatsoever. They do not rely on the cars. So, moving on, we need to actually relate this with numbers or, in functions for numerical representations. So let's say I have a function, f of x. This is an example. F of x equals 3x squared plus x minus 5. So our first goal is, what does this mean? I'm a big advocate for trying to understand what notation in math is actually saying. There's a language that you got to understand. F of x equals 3x squared plus x minus 5. You guys see this as these objects or numbers in mathematics that already have this behavior. However, we have to think more generally. We have to treat this as we understand each notation. So, notice this is the output. The entire thing is the output. The entire thing is the output. Once I calculate everything, I get an output. That is the idea. However, in this problem right here, my function, it's called f. And what I threw in f is this x. If I throw in an x, this function is, in particular, squaring the x. And then is multiplying by 3. But it also makes another copy of that x and subtracts it by 5. And then it's going to add that copy on. So that's the idea of what this function does. If I look at even more abstractly, we can view it as, hey, this is an empty function. I didn't throw anything inside it yet. If I didn't throw anything inside, here's what it's supposed to do. It's supposed to get that object, whatever I throw inside my function, it's going to take it, square it, times it by 3, plus another copy of that object, minus 5. I need to throw something in here. And remember, this f is not multiplying that parentheses. It is not multiplication. This is a notation. This is a symbol of way we're understanding this. So don't see this piece. This is not multiplication. However, over here, this is multiplication. And that's what gets students a lot of confusion. And the reason why the moment you see this f, this g, or whatever, if I tell you it's a function, you have to treat it differently from how you would treat it in mathematics. This is the mathematics that's happening with the machine. However, this is just symbols. These are just symbols for the machine itself. I don't want to mess with that. So I took an x in, and then it does all of this stuff. Great. So, something to try to understand is, hey, what if I were to throw in a -2 with the same f? This is the same f, same function. I'm using the same letter to denote that they're the same function. They do the exact same thing. Well, if I threw a -2 in, it's going to do the exact same behavior as it did with the x. Nothing changed. It's that same rule. It's going to get that -2. It's going to square it. And then it's going to times it by 3. And then it's going to add -2 to itself. And it's going to minus 5. So this is the input. This -2 is input. Now, if I calculate this all out, I get f of negative 2 is equal to 3 times. Now we got to do order of operation. We have to do exponents first or parentheses. So negative 2 times, negative 2 squared is going to be 4, positive 4 plus negative 2 minus 5. Notice that I am not simplifying. I am not trying to calculate the left side. You cannot do anything with that. That's a symbol. You're not doing any math. This is not f times negative 2. I will see that a lot on test. I guarantee you that. And I'll count it wrong. So now we keep simplifying. And notice how I'm showing every step. Plus, what is that, minus 7? And then we have f of negative 2 equals 5. Boom. So if I throw in a negative 2, I'm going to get 5. That's my output. So this is your output. This is a symbol. The entire thing is a symbol for output. Actual value. This is the symbol for the output, the entire thing. However, on the other side of the equal sign is the actual output value. So make sure you understand that. Then I leave it as an exercise for you to try out on this problem, f of 0 and f of 4. Try those out as a little exercise. All right, moving on. Now we get into a little fun stuff. Let's take something called piecewise. Piecewise functions. These are a special type of functions. And sometimes in the real world, we can't really create one function to describe a problem. Not one rule can tell you all the world's problem. So sometimes we have to combine rules together. So let's say I have, a simple word problem like, let's say a phone plan charges $40 for the first, let's say, 300 minutes used. It charges $300 or $40 for the first 300 minutes used. After 300, it charges $40 plus some rate of your minutes. Some rate of your minutes. Now, a piecewise function is going to be a function that has these two rules together combined. So not only am I going to account for the $40 for the first 300 minutes, I'm also going to account after 300 minutes. So let's take it piece by piece. If I wanted to write a function for the first piece, a phone plan charges $400 for the first 300 minutes. That means it's going to be $40 for the first minute, for the second minute, for the third minute, all that. It's going to be a flat fee of $40 the entire time. So if I look at this as a graph, the idea is that this is 1, or let's say this is 10. I don't want to do 10. Let's say this is 50, 100, 150, 200, 250, 300, 350, and then 400. And then we have 10, 20, 30, 40, 50, 60, 70, 80. Let's say we have this, where this is minutes, and this is a function of minutes. I throw minutes inside, and I will get a price out of it. So for the first 300 minutes, it is charging $40. For the first 300 minutes, it's going to charge $40. So boom. It's going to be a constant rate, so it should be a straight horizontal line. This is the function f of x equals 40. Or y equals 40. You are comfortable seeing it as a y-axis. However, I'm not saying y-axis. I'm saying f of x. They mean the same thing, but for our notation, we're going to use f of x equals 40. So this is what your graph looks like for the first piece. Now, the next statement, however, states that after 300 minutes, it charges this rate. It's going to be $40 plus 2 times x. Huh. I have to graph that. But it only happens after 300 minutes. So after 300 minutes, let's say 300 minutes, it's going to be $40. Oops, let's go to 400 minutes. It's going to be $40 plus 2 times 400, which is 840. So it's going to be all the way over here, the price. It's going to skyrocket like crazy. Boom. This is a piecewise function. We have two types of function. We have two linear, but they are combining with each other. We kind of adjoin them. We use the union symbol to kind of combine them together in a way. So how do we write this, though? This seems crazy to write. How do we write this? Well, we can say that the function of minutes, let's use m for minutes, is going to be expressed as, hey, the first part of the equation was only $40. It was a flat fee. There's no rate or anything I have to worry about. It's just $40. But this only happened for the first 300 minutes. So for m in between 0 to 300, this is how much I'm paying, $40. Now, after 300 minutes, so after $300, or 300 minutes, I'm sorry, now you're paying $40 plus 2x. These are your conditions right here. These are your conditions. Conditions. So it's like an if statement here. If m is between 0 and 300, we're paying $40. If it's more than $300, we're paying $40 times 2 times your minutes, or plus 2 times your minutes used. That's the idea of a piecewise function. So it's kind of working with domain in a sense for the first function. Our possible minutes is going to be 0 to 300. But then our second part of our function, our domain is now anything past 300 minutes. So that's the idea of piecewise function. We'll be working more with that later in the units. Now we go into a very important topic. This is called net change. So net change is value of function f as input changes from A to B. So the idea is that, hey, what is the change? What is the value of my function, the change in it, if I change from A to B? If I went from banana to, let's say, strawberry in that earlier example, how much is the vehicles changing? So another good example, let's work with numbers now. Let's work with numbers. Let's say my function is x squared. The idea is if I take A to be 1 and then B to be 3, what is the change? Function change. What is the change? Change as you go from 1 to 3. How much is my how much is my height changing for my function if I move vertically 2 units? So if I went 3 minus 1, what is, which is 2. If I move 2 units, what is the output value? That is the idea. And in this case, if I move just 2 units in my x values, if I move 2 units, Then, let's see, then I have, what is that? 3 squared, it's x squared, yep. But then I'm subtracting 1 squared. This is because remember our function is x squared, so I just plug in a 3 for x and a 1. So how much is it changing if I move 2 units away? Well, my function will tell me that now that I move 2 units away, my function will be approximately 9 minus 1 units away, which is going to be 8 units. So that's kind of the net change. As I'm moving from my inputs, how much am I moving from my inputs? How much am I changing it? How much change is the actual outputs moving? How much input changes and to how much outputs will change. And the last thing I want to do is like a little example to see if we're understanding things with functions. So let's let g of x equals 2x squared plus 3x minus 1. Well, what is f of beta? I just threw a new symbol in. However, my function g, oh, yeah, I made a mistake. This should be a f of g. However, my function g, it's supposed to take in the input x, square it, and it's supposed to get the input x and times it by 3, add those together, and subtract it by 1. This is what our function is doing. Whatever I throw inside my function, it is doing this to no matter what object I am working with. So if I throw in a beta, even though it's a new symbol you guys never seen before in mathematics, this is the exact same thing as saying, hey, I'm going to instead get the beta, I'm going to square it, times it by 2, add it with 3 times that amount, and subtract it by 1. There's nothing different. Your rule still stays the same. So now we can calculate that. Great. Well, if I can calculate that, I can definitely calculate g of a. Well, if I calculate g of a, that's going to be 2, I throw in the a squared, plus 3 times a minus 1. The rule will stay the exact same no matter what objects I use. If I throw in a 0, it'll do 0 with all those objects instead. If I throw in 1, same thing. Nothing special. Now, what if I change it up, though? Well, I can simplify, too, by the way. If I simplify this, I get 2a squared plus 3a minus 1. This is what happens when I simplify it. Well, now I want to go with, what happens if I have, let me use this enumeration. What if I have g of negative a? Well, in that case, I have 2 of negative a squared plus 3 times negative a minus 1. And now these are multiplication, not multiplication. This is not multiplication here. Not multiplication, but these are. So if I calculate this out, g of negative a is equal to, well, negative a squared. A negative times a negative is a positive. So at the very end of the day, I have 2 times a. Oh, this is assuming a is positive. Assuming a is positive, you'll have this behavior. 2 times a. And then plus, well, 3 times negative a. If a is a positive number, that means that's a negative value. So we have plus negative 3 minus 1. If we simplify that, we have 2a minus 4. Okay, so now we have that. Well, let's take it even a step further. What if I had g of a plus h? What if I throw in not just one term, I throw in 2 terms into my function? Well, let's go back to our original function over here. It says we're going to be doing whatever's inside, we're going to do 2 times the squared amount plus 3 times that amount, or whatever's inside, minus 1. Well, now I know what to throw inside. I'm just throwing inside 2 terms. So why not throw inside 2 terms? Boom. But this is this big issue. A lot of people are going to make this mistake. How do you square 2 terms? How do you square 2 terms? You're not going to square a, and you're not going to have a squared and h squared. I'll give you that. Instead, you have to actually calculate it out. This is 2 times a plus h. Remember, squared means you're multiplying by itself. A plus h. You have to do foiling. You have to. Don't try to take shortcuts. So I decided to just, show you what happens if I express this out. I put the brackets after I foiled it out. I can foil these guys out and everything like that. I put a bracket so I can show that's multiplying by 2 from above here. And then you should get this expression. Now I had to, after I foiled it out, I distribute this 2 all over to each of these terms. And I get all of this mess. Okay? Now, this actually has a very good story. G of a plus h. It's saying if my input moves by a specific h value, like let's say a was 3. What happens if I moved it by 2? Well, that expression is exactly going to be over here. If I move only 2 units away from your value a, I'm going to get this new expression to calculate that. And that's going to be the output. That's how much my output will change if I move it by h. Now, something that's very important in calculus is called the difference quotient. It is exactly this. G of a plus h minus G of a all over h. This idea is the change in your inputs. If I move the inputs by h, how much is my outputs going to move? If I had an input a, but then now I have an input that got h added onto it, what is the difference in their output? How much did their output change in comparison to how much I moved their inputs? So this idea, and of course h cannot equal to 0 because you don't want to divide by 0. This seemed like a lot of mess and everything, but thankfully we did all the scratch work. We have this. We have this. All we have to use is the previous answers to make our life easier. So if I plug this in, I get 2a squared plus 4ah plus 2h squared plus 3h plus 3h minus 1. Now I got to add in the g of a. G of a is 2a squared plus 3a minus 1 plus 2a squared minus, or plus 3a minus 1. And now you got to be careful actually. So let me erase this. I got to actually be careful. I made a mistake here. This is subtracting 2a squared minus 3a plus 1, or minus 1, I'm sorry. Plus 3a minus 1. All right, so to deal with subtraction, I'm going to turn this to addition, but I'm going to change the sign of everything. So this is all over h. And if I change the sign of everything, I now have 2a squared plus 4ah plus 2h squared plus 3a plus 3h minus 1 plus negative 2a squared. What is that? Minus 3a plus 1. After I turned it into addition, I had to change the sign all of my right expression, all over h. But you notice that we can find combined like terms now. 2a with negative 2a squared. What other like terms do we have? We also have, let's see, we have positive 3a and minus 3a. We also have plus 1 and minus 1. Well, things are playing out nicely because if you notice, this cancels out with this cancels out with this. They get zeroed out. This cancels out with that. So all we're left with is 4ah plus 2h squared plus 3h over h. And then it looks like you can't simplify anymore until you realize these all share an h in common. So you have to find the GCF, which is just h. Then if you take a factor of h out, you get 4a plus 2h plus 3 all over h. This is now multiplication. You have one term, and it's just multiplication of the factors. H cancels out. You're just left with 4a plus 2h plus 3. That's a very powerful thing because I'm saying over here, if I wanted to see how much my function will, I guess, vary if I slightly move my value, my input by h, if I slightly move it by h, then my output in particular will be this exact amount. And this is not that big of a change for our problem in particular. Some problems will have a bigger output change. It's the idea of, hey, my input was originally A. If I slightly move it a bit, let's say 1 unit further, how much did that affect my outputs? And then affected by this exact amount. That is the idea of the difference quotient. Is seeing how a function is sensitive. How sensitive is it? If I slightly perturb it, does it explode? Does it barely move? That's the idea. So I'm gonna leave off today. I will see you guys tomorrow on 2.2. Take care. Bye.